So let's go over some of the Minds on Physics graphing sets of questions, and there's 11 of them, right? And so kinematics graphing 2, kinematics graphing 1 is basics, kinematics graphing 2 is interpretation of position time graphs. And this one comes with the question, during which time interval is the object moving with the greatest average velocity? So before we answer that question, let's just examine the position time graph and interpret these different lines. So if a line slopes up, it means the position at every next time interval, the position is increasing. And since the slope of a position time graph is the velocity, or the magnitude of the velocity of the speed, the slope of the line will indicate the speed. So here the slope is maybe 1, so the speed is 1. Here the slope is 0. Notice the object over this time interval is sitting in the same position, right? It's at rest. Its velocity is 0. Here the slope is steep, so in a very short time interval it covers a big change in position, right? So this would be the one where the speed is high because the slope is high. Here's another one, section D, where the object isn't moving, right? It's sitting in a position. So this is how you interpret these. And here's one, it's a little hard to see maybe, but the slope is about 45 degrees. This might be 80 degrees, and this might be 60 degrees. So I'm seeing this is the least slope. This is, well, except for 0. This is the most slope, and this is an in-between slope. And what's the difference here? Well, the position is going from some positive position back towards 0. So the object's moving backwards. But since the slope is constant, the speed would be constant over this interval. And so this is a negative velocity, but since the question is which interval shows the greatest average speed, it would be interval C. Now notice F is also not changing. The object is at position 0 and it's sitting there. And then what happens? We see a curve. So the slope of this is changing, right? It starts with a low slope and goes to a bigger and bigger slope. So here we have a position time graph showing increasing speed and increasing, well, increasing in a negative direction. Increasing speed would be an acceleration, but a negative acceleration. So a flat line is 0 velocity. Any sloped line is a constant positive or negative velocity in proportion to the slope. And a curved line, a parabola, right, we've seen this before, indicates an accelerating object. Okay, let's try another one. Okay, here's another one taken from KG2 with a variety of sections. And any number of questions could be asked. The one I'm seeing right now is, during which time intervals is the object moving with a negative velocity? So rather than just answer that question, let's step through each interval and see what's happening. So pause the video and step through each interval and make a mental note or write down what's happening. Pause the video and then come back. It'll work much better if you don't just listen to me, but do the thing yourself. Okay, here's what I came up with. During the A interval, it's sitting in a negative position, but it's not moving. So this is like minus 30 meters, and it's sitting there. So it doesn't have, even though it's in a negative position, it doesn't have a negative velocity. It has a velocity of 0. Now it goes from a negative position to 0. So the key here is the slope is positive. So it's moving with a constant positive velocity, which is the slope of the line. Actually, it would be useful to go back to our basic equations for velocity at this point. So notice that V average is the change in position with the change in time. So the final position minus the initial. So if we take the final position of 0 and we subtract the initial position, a negative number, we get a positive displacement. Okay, and that leads to a positive velocity. And since the slope is constant, the average velocity will give us the instantaneous velocity, because the instantaneous velocity at any instant is this ratio of changing position to time taken in the limit as delta t goes to 0. In other words, where we have a curved line, the slope is going to be a tangent to the line, and the slope is going to change. So anyway, let's proceed with that in mind. C, obviously you're sitting at a position of 0 and not moving. Now D, notice, it starts out where the position is increasing, but then it increases more and more. So if we think about the slope of a curved line as being a tangent to the line, the tangent to this starts at 0, and that tangent line increases. And so this is an indication of a increasing velocity, and the slope of every point on this line is positive, so there's no negative velocities here. And now it starts to curve down, which means the slope of the line is getting less and less and goes back to 0. So even though this is curved down, the derivative or the tangent line or the slope of the line at every point is either positive or 0. And then here, obviously, you're sitting at some positive position and not moving. So there is, in fact, no place on this where there's a negative velocity. So moving ahead to KG3, here's a series of lines and a diagram that you might see, and there's usually a question associated. The question here is write the letter for the object that has the greatest constant velocity. Consider absolute value only. So we know from previous examples that the greatest velocity will be the greatest slope. And so the answer to that would be E. And if we go through this, we can see that A is in a positive position, but the velocity is 0. It's not changing position. And C is at a 0 position. And if there were a straight line down here in the negative, it would still be 0 velocity, because a straight line means the position isn't changing. This is a positive velocity, 0 velocity, negative velocity, and more negative. And since the slope of these two lines are about the same, the line with the greatest slope is E, and although it's negative, the question says consider the greatest possible, the magnitude of the greatest possible constant velocity. And these are all constant, right? There's no curved lines. Okay, there's another set of lines. Pause the video and go through the lines A through E and decide what you can say about them, and then come back. Oh, and the question, it could be any question really, you should answer all of them, but which object is moving with the smallest constant velocity? but just address each graph and understand it. Okay, you're back, you answered the question. So constant velocity has to be a straight line, right? And C has a slope of 0, and the only other straight lines are B, which has more slope than D. So this has the smallest constant velocity, either, especially considering magnitude, it's negative. And A has a changing velocity, right? It's an accelerating object because the slope of the position versus time. So this starts out with velocity of 0 and increases to a maximum velocity here. And this also starts out with velocity and increases to a maximum negative velocity, but it's never constant. The curve means that the slope or the velocity is always changing, increasing, either positive or negative. So KG4 is just some graphs with numbers where you're calculating the slope, and the slope, when the line is straight, is simply the change in y over the change in x. So this slope changes by 8 minus 2, 6 units over 4 seconds. So 6 over 4 is 1.5 meters per second. And this goes, final position is 10 minus 8, it changed by 2 over 10 minus 4, 6 seconds, so 2 over 6 is 1/3. So this has a slope of 1.5 meters per second, and this has a slope of 1/3 meters per second. Okay, KG5 is basics of velocity versus time graphs, and KG6 offers a series of graphs such as the one I'm showing you. So again, there could be a wide variety of questions asked about this, but let's pause the video and go through all 6 sections and see if you can decide what the characteristics of each section is. So pause the video, do that, and come back. Okay, so a reminder, acceleration is a change of velocity over time. So the change in velocity over the change in time, and this is average. But since there are no curved lines, the average and the instantaneous will be the same. So now the slope of the line, the velocity time curve, is the acceleration. So this is a positive acceleration. 0 acceleration. Notice it's moving through space because the velocity is constant. So notice the difference from the position time graphs. This, the velocity is getting less and less, going to 0, and then getting more and more negative. So notice this is a negative acceleration. And it's useful to think, what's an example of this? You throw a ball up and it slows down, and then it comes down and it speeds up. So notice the acceleration is negative and constant, and it reaches a point like throwing the ball up where it's the top of the path. The velocity is 0, but the acceleration is not 0. That's an important point. And then down here it has a big negative velocity, but it's constant. So it's actually moving very fast in the negative direction, but it's not changing. And then moving very fast in a negative direction, what does it do? It slows down. So it's moving fast and it slows down until the velocity is 0. So it's useful to be able to picture real situations. And so notice this is a positive acceleration. Even though the object is moving this way, it's slowing down, so the acceleration's in the opposite direction. And a good way to understand that is an object moving fast this way that slows down has to have a force pushing in the opposite direction to slow it down. So the force, as we'll learn later, and the acceleration are always in the same direction. So what do we have? Constant positive acceleration, zero acceleration, a constant negative acceleration in both these sections, because the slope doesn't change, a constant, it's zero acceleration with a constant negative velocity, and then a constant big negative velocity going back to zero. Okay, KG7, interpreting more velocity time graphs. So pause the video. There's a series of wide variety of questions that we could ask about these graphs, but just pause the video and go through each line and remind yourself what it's showing, what kind of motion it's showing. Okay, let's go through them. So A is a constant positive velocity, right? The velocity isn't changing, so A has a constant positive velocity and no acceleration. B has a velocity that starts at zero and increases constantly. So it has positive velocities, but they're increasing. And the acceleration, the slope, it's a straight line, so the acceleration is positive and constant, right? Because the slope is constant. And C has the same slope, so it has the same acceleration, but it starts with negative velocities. And the negative velocities decrease to zero and then increase. So it's kind of like an object moving fast this way and slowing down and stopping and bouncing back and increasing in speed. So it's good to go through these. Make sure you should visualize an object moving in this way. And E starts at zero. It's supposed to start at zero. And the velocity gets increasingly large in a negative direction. So that would be something starting here, moving in this direction, and speeding up. But it's a straight line, so it has a constant negative acceleration because the negative velocity is increasing. And the slope of this line is less than the slope of this line, so it's a smaller acceleration in terms of absolute value than B and C. F has a bigger negative acceleration. It starts at a bigger negative velocity, but it rapidly changes to greater and greater negative velocities, and then it becomes constant. So this starts at a negative velocity, the velocity becomes larger, it reaches a point where the velocity stays constant. So that's actually capturing two kinds of motions, and the acceleration is also negative because the slope of the line is negative. And this is the biggest absolute value acceleration of all of them. Okay, so if you know all that, you should be able to answer all the different questions that are asked about these graphs. So in KG8, you're going to see basically two kinds of graphs. One that starts at zero and goes up to some value, and then the velocity becomes constant, and others where the velocity is increasing at a steady rate, but we look at different intervals of that motion. So I think you're well enough familiar with the fact that the acceleration is the slope of the velocity. So if the slope is zero, the acceleration is zero, the velocity is constant. In this case, the velocity goes from zero to some value over this period of time, and by finding the slope you can find the acceleration. So I think we've covered that. What comes up here is during the period, supposing this is, let's put some numbers in here. Okay, a little bit hard to read, but anyway, this is 4 seconds, this is 6 seconds, this is 8 meters per second. This is 6 seconds, this is 10 seconds, this is 2, 6, 8 meters per second. So now the question might come up like, how much distance does this cover when it goes from 0 to 8 meters per second over 4 seconds? And so the way to think about that mathematically is, since the velocity is changing, we would take the average velocity over that time interval and multiply it by the time, right? That equation would be delta x, the distance covered, would be the average velocity times the time. And the average velocity in this case would be the final velocity minus the initial velocity. So 8 minus 0 divided by 2, it would average 4. And so you would have 4 meters per second, which is the average velocity over 4 seconds. And notice I'm canceling the units and I'm getting 16 meters is the distance covered. So from a calculus perspective, the acceleration is the slope of the line, but the distance covered is the area under the curve. And if you're in Calc 1 and haven't had this, I'm going to show you how this comes out of calculus and the idea of the integral. Okay, so things are getting a little crowded here, but just try to follow this. So we know our definition of velocity, instantaneous velocity, is dx dt. So if we rewrite it, if we want the x, we multiply velocity times time. But the velocity is changing. But if we do it for a very short distance, the velocity doesn't change much, and we get a dt. So in terms of the graph, that's like calculating the area, a very small area. And so when you study the integral, you'll see you create these little areas and you add them up. This is the idea of the integral. So if we add up all the dx's, that's what the integral is. The integral is a summation of infinitesimal parts, and we integrate the velocity times the time, we get the actual value. So when you get to Calc 2, you're going to learn this. For our purposes, you can use here, you can use the idea that it's the average velocity times the time gives you the area under the curve, or you can use the idea of the area under the curve. So this is a triangle, and the area of this triangle is 1/2 the base times the height. Well, what we did was, when we took the average, we took 1/2 the height times the base, which is the same thing, and we get the area. So either by using this equation or by calculating the area, you can find the displacement. So if you come to a place where the velocity is constant, it's 8 and not changing, and it moves at that rate for 2 seconds, you simply multiply the 2 times the 8, and you also get 16 meters. So it covered 16 meters during this interval and another 16 meters during this interval. If we come over to this one and we want to get the distance it covered, well, it started at 2 and it went to 6. So the average velocity during this interval is 6 plus 2, 8, divided by 2, that's 4. So it's averaging 4 over 6 seconds. So if we do, using this, if we take the average velocity of 4 over a period of 6 seconds, we would get that it covered a distance of 24 meters, and that would be the area under the curve. You'd have to break it into a triangle and a square and add those areas. If you wanted to know how much distance it covered during this interval, you'd do the same thing. you take the average of 6 and 8, which would be 7, and you would multiply it by the time going from 6 to 10 seconds, so it would be 7 times 4. You would get a distance of 28 meters covered during this interval. Okay, so that's KG8. Okay, KG9, we have a series. So there are two major parts of this: position versus time graphs, matching the motion to oil drop diagrams. So we have 6 different graphs of position versus time. Be careful, position versus time. What would be, this is a little bit, you're not picking, anyway. So go through each of these graphs and make a chart like this on a piece of paper and draw the oil drop pattern and the direction, right, onto the diagram, so that way you can match any of these to the correct oil drop diagram. So pause the video, fill this out, and then come back and see how you did. This is a good learning exercise. These are great diagrams, and likely I'll ask you this on the quiz. Okay, this is something of a challenging question. Let's see how you did, and even myself, I want to be sure as I go through these that I didn't make a mistake, especially since I have a mistake in the video. It's pretty bad because it's hard for me to, I don't really know how to fix it. So let's go through M and let's talk it through. So we're in position versus time. So the velocity is the slope of the line. So this has a big positive velocity, and as time goes on, the big positive velocity goes to a slope of 0. So M would be moving in a positive direction, right? The position is getting bigger and slowing down. So the oil drop diagram would look like that. Now N is a straight positive line. So in a position time graph, be careful, a straight line is a constant positive velocity. So it's a positive velocity, has to be moving this way, and the oil drops should be equally spaced. I'm not that good at drawing them perfectly equal. So P, notice P starts at a position and goes to smaller positions. It goes from like 100 meters to 50 meters, you know, going towards 0 meters. So the slope of this line is 0, and then the slope gets increasingly negative. So this has to be moving in a negative direction, and I should have more dots here. It starts out at 0 velocity, and then gradually the velocity increases, so the dots should be getting further and further apart, and if you look at this, they're not further apart. So it's not drawn that well, but it is moving in this direction, and the speed is increasing in the negative direction, right? That comes from the negative slope. Q starts with a velocity of 0 and becomes increasingly positive. So this is an accelerated motion. The velocity is the slope. And so if we go to Q, it's moving in a positive direction, and the velocity starts at 0 and increases. I should have a bunch of dots there because it doesn't really show that it's starting at 0. And S starts with a big negative velocity. Why? Because the slope is negative, and then the slope goes to 0. Right? The slope of the curve is the velocity, the dx dt. So the position is getting less, so it has to be, I'm doing S, yeah. So it has to be in the negative direction. and that means it's moving this way. And so it starts with a big velocity, and that velocity gets smaller and smaller until it reaches 0. And then I skipped r. R is a constant negative velocity. The slope is constant. So r has to be negative, and the oil drops, like the ticker timer, should be equally spaced. Okay, I don't think I made any mistakes. That all seems reasonable. Now let's do this for velocity versus time graphs. So now we want the oil drop patterns for these 6 lines. And we're looking at velocity versus time graphs. So think about what kind of motion these represent and what kind of oil drop patterns or motion diagrams they would lead to. So for velocity time graphs, the acceleration is the slope, right? So the first 3 all are positive velocities. They all lie above the 0 line. And so all those 3 will be moving in a positive direction because the velocities are positive. Now in the case of A, it starts at 0. That doesn't really show it starting at 0. It should be a little more crowded. But anyway, it starts at 0 and the velocity gets bigger and bigger as in a positive direction. And B is a constant velocity that are positive. So the dots are even and the direction is this way. And C starts with a big positive velocity and goes toward 0 in this direction. And these are just kind of these are all below. So if we take D, D starts with a big negative velocity which gets less and less, approaching 0. In the actual graph it goes almost to 0. Here it doesn't. And E are all negative velocities, so it has to be moving in the negative direction, but the dots are evenly spaced because the velocity is constant. And F starts with 0 velocity and becomes increasingly negative. So it's moving in this direction, and the dots are going to be further and further apart. Okay, we're skipping KG10. Now we're on the last one, KG11. And it asks you to match velocity time graphs with position time graphs. So these are different position time graphs. And so pause the video and see if you can match each of these graphs to one of these graphs. And then come back. These are tricky. Let's see if I got them right. So A starts at a velocity of 0 and goes to bigger and bigger positive velocities. So the position versus time graph, the velocity is the slope of the line. So this starts at a velocity of 0 and the slope gets steeper and steeper. So 4 aligns with A. B is a constant positive velocity. On the position time graph, a constant positive velocity would be a straight line with a positive slope. F is a constant negative velocity. That would be a straight line with a negative slope. C starts with a big positive velocity and the velocity goes to 0. So here the velocity is the slope, so it starts with a big positive slope, and the slope gets less and less and goes to 0. But these are all positive slopes. That one's tricky, I thought. And E starts with a big negative velocity and goes to 0. So notice the slope. The velocity is the slope. The slope is big negative number, and it gets less and less a negative slope, and it goes to 0. And g starts with a slope of 0 and goes to a big negative slope. So that's the matching on that one. Okay, finally the last one. Now we have back to our position time graphs. We have 6 of them and 6 different velocity time graphs. So now we're matching these velocity time graphs to the corresponding position versus time graph over here. So go ahead, give it a try, and then come back and see what I have to say about it. So remind yourself, on the position time graph, the slope is the velocity. And so we're matching slopes over here as you did in the last one, but it's the reverse direction. So on 1, we have a velocity which is constant and positive. So that's b. This is supposed to be a straight line, by the way. So this has a constant positive slope. The slope of this line is positive and constant, so it matches that. And E has a straight line with a constant negative slope, so that matches that one. Constant negative velocity. And 3 starts at a velocity of 0 and goes to bigger and bigger numbers. So d, the slope of this is 0. Then the slope becomes increasingly large in a positive direction. So d matches this one. Here we start at 0, and the slope becomes more and more negative. So that would be c, starting at 0 and become velocities that are more and more, bigger and bigger negative. And 5 starts at a large positive velocity, which goes to 0. So the slope, right, it's the opposite. This goes from 0 to large, but the slope is large and positive, and the slope gets less and less and goes to 0. So this would be A, and this starts with a big negative slope, and as you go down, the slope goes more and more towards the slope of 0. So here the velocity starts with a big negative number and goes to 0, and that's what F does. Okay, I think we're done. Last but not least, the table of contents. So we have all the different kgs that I covered, not all of them, and the times at which you can find those on this video. So I didn't know the table of contents till the end, so it's published here at the end. It might be useful to you if you're just looking for a particular set of kgs.